I'd like to welcome our final speaker this morning. He's Thomas Gutsmann from the Leibniz Lung Center and University of Lübeck. Thomas did his studies in physics at the University of Kiel. He's also spent 2 years at the University of California in Santa Barbara, working on the construction and use of atomic force microscopy. Since 2010, he has been a professor at the University of Lübeck, and his research is focused on the role of lipid membranes in bacterial disease of the lung. And he's going to talk to us today about bacteria on the flight. Thank you, Thomas.
Okay, good afternoon, everyone. Thanks a lot for staying here for the last talk of this really great conference. And I'd like to especially thank the organizers for inviting me and putting up this great conference. I learned a lot within the last 3 days here in Edinburgh. And I will kind of continue with the talk from Leanne in the morning. So, okay. You just have to exchange 2 things. Number 1 is we didn't work with plastic particles, but with bacteria and Sahara dust. And the second one is we didn't went to the island in Croatia, but we went to an island called Cape Verde Islands in the Atlantic Ocean. So I will explain you in a minute why. So since the pandemic, we always have these discussions, how far can bacteria or viruses travel? We all have in mind that is it 1 meter or 2 meter, what is a safe distance if one person is infected? We know that, for example, in tuberculosis, patients in the same room can infect each other. We also know from Legionella disease, especially in cooling towers in different cities, there are always outbreaks 1 or 2 times a year in Europe, that Legionella bacteria can travel some kilometers depending on the weather conditions. But can they also travel more than 100 kilometers? And before I come to the Cape Verde Islands, I will explain you one question I always got in the last 2 days. The research center Borstel, where is Borstel? You can see it here. It's up in the north of Germany. Here's Hamburg. And here, that's the location of the research center Borstel, the Leibniz Lung Center. And it's really in the countryside. Here you can see it's pretty green. And the reason was quite simple. It was founded as a tuberculosis research center, and we tried to get out all patients from the bigger cities 76 years ago to treat them and not to spread tuberculosis anymore in the bigger cities. So tuberculosis is still a big issue in our institute. We host the National Reference Center and the WHO Supranational Reference Center for Mycobacteria. But groups are also interested in all kinds of infections of the lung and of chronic lung disease. And we work together in a very interdisciplinary project together with other groups in the Leibniz Society and on the Cape Verde Island, and it's called Dust Risk, Risk Index for Health Effects of Mineral Dust and Associated Microbes. And the reason is quite simple. As you can see here in this graph, that's the dust deposition, and as we heard in the second talk this morning, that even in Western Europe, dust particles from the Sahara dust can spread to North Europe. There's a special dust particle exposition here in this area, and the Cape Verde Islands are located here. So, as we also heard, many diseases are somehow related with pollution and with dust, and especially on the Cape Verde Islands, people in the hospital figured out that around January, February, many patients have an infection within the lung, and exactly at that time, the Sahara dust brings the dust particles to the islands. So we try to figure out what happens. So the dust comes from the Sahara. It picks up maybe microbes, flies over to the Cape Verde Islands. There are some processes taking place within the atmosphere, ROS production and so on, and then they're exposed to humans and they inhale the dust particles and maybe also the microbes. And we want to know if there is a correlation or not. First of all, you can see here in purple the dust plume within the Sahara dust in February, and you can see here in these slides that's a real particular problem in these 2-3 weeks in January and February. So we established different sites on the Cape Verde Islands, on 2 islands, São Vicente, here one directly at the coastline, one in Mindelo, and one at the airport, and on Santiago, one here at the coastline again, and one in the capital, Praia. As I said, it's a very interdisciplinary project, and we try to understand how it all interacts. So we collect the dust samples and the meteorological data in field studies. And then in the next step, we investigate the dust, the chemicals, microbials, the toxicity of these compounds, and the interacting properties. We try to link these properties to the source of the region in model studies, and of course also the hospitals and criminologists on the Cape Verde Islands are involved in the impact of dust on illness in the clinical and epidemiological studies. So all these people are involved from different institutes, and Vadinga Womba, he's the speaker of the whole consortium, and I will show you some results from all of these groups. So first of all, to give you an impression how it really looks like, if we sample, here these are the cyclones where we sample the dust, one part of it. That's in February 7th, so it was a clear day, and 1 week before there was the Sahara dust, and you cannot see very well. So you collect the samples, and we calculated in a simulation how the dust is distributed, and this one here is a measurement, a so-called LIDAR, Light Imaging Detection and Ranging experiment, where you shoot with a laser into the sky, and then you can measure over time the distribution of the dust particles in the air. And you can even see here a nice correlation with the simulation, and there are dust particles especially up to 1 kilometer, but also up to 3 kilometers. So the question is, does these dust particles somehow influence the health of the patients? And here, that's the time schedule, and here that's a reference period without the dust, and then here we have a dust event, and that's the oxidative potential of the dust measured in a cell experiment, and you can nicely see here that we have in the dust event an increase of the oxidative potential as a metric for quantifying particle toxicity. So that means there is a toxic effect. So if bacteria interact with the human immune system, they normally stimulate immune cells, for example, with IL-1 beta. And one of the most potent stimulator here is LPS, or endotoxin, which we used here as a control. And this one here is just quartz dust, which was not infected, or which was not from the dust. And here you don't see any effect. LPS is a positive control. And if we add the Sahara dust to an air-liquid interface co-culture model here, you can nicely see the increase of the inflammation in the cells. So there is an activity on immune cells. The question was, is it due to organic or inorganic constituents of the dust? And here you can see if you bake the Sahara dust, the effect is dramatically reduced. So we assume that this is because of an organic or from the bacteria resulting constituent, especially the lipopolysaccharide. And then you have seen such a setup this morning with an Impinger, the bioaerosol sampling, and then the samples were cultivated already on the Cape Verde Islands and then shipped to Germany, and we compared the microbiome from the Cape Verde soil just as a reference. Maybe it's only an effect of the soil on the islands, but you can see here that the pattern compared with the Sahara dust from the filters is different. So that's the reason why we assume it's not only an attachment from the soil, but already from the Sahara dust, picking up microbes on sea spray on the way to the islands or even already in the Sahara. So that was more a global question, and now we go down to the molecules. We try to understand how the bacteria couple to dust, how specific the binding between dust particles and bacteria is, and how does co-aggregation contribute to transport and protection of the bacteria. So for that, we use the bacteria we isolated from the dust particles. We take the dust particles, incubate them, and then we have well-defined particles, or we can even take the particles from the dust storm, taking out of a filter, shipping it to Germany, and then we use an instrument, and you already mentioned that I learned this in Santa Barbara at the University of California. It's called atomic force microscopy, and I guess it's not a very familiar technique here in this audience, so I like to explain it shortly. It's a microscopic technique, but we don't use really light to image the sample. In this case, we have a small cantilever, so it's like blind people can read. You can feel the surface, and in this case, to feel the surface, we use a so-called cantilever here with a very, very tiny tip, and at the end we have only some atoms, and we have different geometries, and we can measure the bending of the cantilever while attaching to the surface. And that's a nice technique to image samples, so we can image whole bacteria. You can see the flagella here. We can image individual molecules like these DNA molecules, and the big advantage is we can do these experiments at very high resolution, at atomic resolution, also in buffer, so under natural conditions. And we can even go down to the atomic level and image individual atoms. We cannot only use it to image, but we can use it to do so-called force spectroscopy experiments. So we go down, press on a protein or a bacterium or whatever you have on your sample, you press on it and you pull on it, and when the force is strong enough, the bond breaks. And here in this graph you can see now you stretch the bond and it breaks, and you can measure the binding between individual molecules, so single molecules. And we did this for the bacteria, and here you can see conventional scanning electron micrographs of the dust particles. Some really look like, have this mineral look, and some are more this organic look. So it's a mixture of organic and inorganic material, and we can also see this in element analysis. We also incubated the dust with different bacteria to have well-defined structures, and you can see here the dust particles with Staph aureus in this case. And then in the next step, we imaged the samples, and you can see here, without going into too many details, that's the height image, and this one here is a so-called phase image, where you can see that the dust particles have different domains of stiffness and different mechanical properties. And when we add the bacteria on top of the cantilever tip, one bacterium, and we have the dust particle, then we go down and measure the force between the bacterium and the dust particle. Now we can do this, and then we get curves like this. So we go down, that's a red curve here, we go down, press on the dust particles, go back, retract, and then we get these nice little curves here and here. And if we zoom in, it looks like this. So these little steps here are really the breaking of individual molecular bonds. And from this, we can calculate the binding force and make these histograms. And we came out that we have here a very weak binding force of about 70 piconewton. just to give you an idea, a normal antibody-antigen interaction is more like 300, 400 piconewtons. So this one here is a rather weak interaction, but we can understand that these bacteria can nicely adhere to dust particles. And we used to generate kind of reconstituted aerosols, we use these sparking liquid aerosol generators. We use the Goldberg drum to simulate the aging or influence of the time, temperature, humidity, and UV light. And then we sample them with an aerodynamic particle sizing or with an Anderson cascade impinger and image them with an electron microscope. We determine the CFU, how long these bacteria can survive under different conditions. So coming back to the idea of the tuberculosis bacteria, just to show you and give you an idea that nature is sometimes a little bit more complicated. If you have a patient having tuberculosis, he normally coughs out not the single bacteria, but they are always integrated in some cells. And so we try to simulate this by using neutrophils. Here, that's the neutrophils, and these are infected neutrophils with Mycobacterium bovis. And then we use necrotic neutrophils, which is the most likely situation in the tuberculosis patient. And we made an aerosol out of it, and we measured it in the impinger, and we measured the surveillance or the survival of the mycobacteria within these different cells. And you can see they clump, they form bigger aggregates. But what you can see here in the necrotic neutrophils, the bacteria can survive better. So that means that the surrounding, if it's a dust particle or if it's human material, can lead to a different survival of bacteria. So to summarize all this, I haven't talked about viruses, but we also did some work with virus particles. So influenza and also SARS-CoV-2, of course, transmit over short and long distances, especially influenza. Depends on the weather. If it's we need the right ambient humidity, when it's low in wintertime, you normally have these conditions where the viruses can survive pretty long. M. tuberculosis transmit over a short distance. It's more like a meter or within a room. And also here, the humidity between 60 and 80% is protective. And the Sahara dust particles can transmit over probably even hundreds of kilometers. And we are not quite sure how they can survive, because you also have the UV light on this journey, but also the amount of water surrounding these dust particles is important. And that's the next step in our investigation. So to answer the question, bacteria and viruses can travel short distance and unfortunately also long distance. Thank you very much.